let me say that anything you say in the workshop can be minuted and published in the conference proceedings free of charge. So the way I'll handle that is if you want anything to be minuted, then send me an email. I'll send you an email asking for it. Send me an email of what you want to be minuted, and then it can be published as part of the conference proceedings. And I think it's useful that we have a conference part and a workshop part to the proceedings. I'm very much in favour of allowing people to express, giving a forum where people can explore new ideas that wouldn't normally be admitted to a scientific conference. So that said, Mark, you've said you want to say something. Does anybody else want to say something about the work they've been doing recently? Tiago, Walter, Yanni?
Let me say that I may have to quit earlier
Okay.
than the endpoint of this thing.
No problem.
No problem.
Tiago, is there anything that you want to say in the workshop part about work you may have been doing?
Yes, I don't have news about my research about transmathematics, but I have a news. Last week, I gave a workshop about transmathematics in other institute, not my institute, but in other universities, for undergraduate students of mathematics and physics. It was nice, the workshop.
And how many people were at the workshop?
About 30 students between mathematics and physics. And they were interested in the application, the use of the transmathematics in computer. And I suggested him their look for your papers and the channel and the YouTube, because I don't know to talk very well about the applications, only about the math.
Let me give you the big application to computing, which is if you take IEEE 754 floating point arithmetic. It has a lot of nans. It has 64-bit version has 9 quadrillion nans. This is roughly 10,000 per star in the Milky Way galaxy. It's a lot. It's enough to double the accuracy of a floating point calculation. So if you remove all of the nans and replace it with one nullity, then you double all floating point calculations using the same number of gates in silicon, more or less, and exactly the same memory.
And also the same time?
Exactly the same time.
Okay.
We have done a floating point. So 2's complement is a little bit slower. Floating point is the same time.
And why do people not take this important message as a fact that influenced technology?
There is a lot of momentum behind existing computer systems. And a lot of businesses, for example, IBM and Intel, their business assumes that you can take pre-existing source code, recompile it, and get the same result. So they can't afford any move away from the standard. However, there are points in history when people have moved away from the standard. Most recently in parallel computing, floating point arithmetic has some properties which make it extremely expensive in parallel computing. So it is better to remove some of its features. And you gain huge advantages by doing that. Recently, people have gone to the expense of putting those floating point features back into parallel processing elements. So they've increased the cost of the chips, they've increased the power consumption. It's a retrogressive step. Now, the standard is an industrial standard. It describes what the industry does. Any company that produced a floating point unit using transreal arithmetic would then have a huge marketing opportunity. They could say you can use an Intel chip with 9 quadrillion errors, or you can use one of ours with none. You can use an Intel chip, or you can have twice the accuracy. So there is a huge marketing potential to whoever is the first company to switch to transreal arithmetic. And this is not an idle claim. I was consulted by a manufacturer of embedded systems, and they said that the twos complement, trans twos complement arithmetic, would improve all of their devices, typically reducing the footprint in circuitry by 80%. And the reason for this is obvious to me, not to the world. So for example, if you take an inertial navigation system, you use twos complement, there is one more negative number than positive, and so you tend to go round in circles. In order to correct for this, you need some circuitry to account for that fact that you've got one more negative than positive. You can't use any existing computer chip to do that because they all work the same way. So you have to use bulk circuitry, resistors, capacitors, and so on, to correct the computer chip. And those corrections in inertial navigation systems take up 80% of the die area of the device. And they consume a lot of power, much more power than the chips. So there is huge advantage to moving to these. And the company I was consulted by spent quite a long time looking at this. They spent 6 months on it, and they said every single product we make would be better with trans twos complement, but we can't do it because first of all, the hardware doesn't exist and there's no software stack. Now, there is an easy way to get to that happy position, which is if the manufacturers of FPGAs would support trans twos complement arithmetic, then suddenly those advantages would be available. You wouldn't get all of the advantages of an ASIC, but when you've got 80% wastage, there's plenty to go for. FPGAs are a second way that transreal arithmetic might reach the tipping point.
I actually work with a guy who is big in FPGA and is creating software for opening up a kind of an open source approach to FPGA. So this is very interesting to know about.
If you could put me in contact with him, then we could have a chat.
Absolutely.
Walter, do you have anything you want to tell us before we move to Mark? No. Okay. Mark, the floor is yours.
Yes, and also as Jan, I will have to leave in perhaps half an hour or so.
Sure.
So thank you for giving me the first slot. So apologies to everyone. I haven't prepared anything. This is very much off the cuff. So what I'd like to just tell you a little bit about what I've been doing the last two, 3 years in my spare time. This is somewhat related to what Jan began by saying about promise theory. And for those of you who didn't arrive at the beginning, I'll just repeat a little bit about what promise theory is. Excuse me. So promise theory is basically a story about agents, autonomous agents, where an agent is a thing which can have some internal resources, some memory, some computability, can make decisions perhaps, and it can decide to make promises to other agents, where a promise is some kind of signal about its intention to act in a certain way. Agents are only allowed to promise their own behavior. That's what makes them autonomous. So we can't force something on another agent. And if you reformulate the story of the world in terms of agents, autonomous agents, some very interesting things happen. This is, of course, quite different from the story that Newton created for us, where you have bodies, things which are featureless. Usually just a center of mass point is the basis of Newtonian mechanics. And these things, all the behavior of these things is externalized in a space-time, which is a kind of a theater and coordinate system in which things move around. And all of the states that we can accomplish involve moving bodies around to different positions and different times. But there's another view of the world in which in which space and time can have interiors and exteriors. Going back to the discussion that well, everyone has been talking about, really. And this is the world of agents. So an agent has some boundary or some border, and what goes on inside stays inside, but that which is externalized to the outside becomes, or which is promised to the outside, becomes observable by other agents if they choose to do so. So in a world of agents where promises are made, and promises are made to accept promises of other agents, because autonomy means that they have to officially accept as well, then we have to extend our view of the world to describe interior processes and exterior processes. And what I do is I take this promise theory of agents, and when there's a binding between an agent, there's an offer by one agent which is accepted by another agent, there's a binding. And it's a unidirectional binding. It's not a symmetric equivalence relation yet, it's a unidirectional thing. But it requires the cooperation of two independent parties to make that happen. I call them plus and minus. So a plus is an offer and a minus is the acceptance of an offer. And these things have some structure as well. So I may offer you a set B of possibilities, and you may respond, I'm willing to accept B prime. And then the equivalent overlap is B intersection B prime. And so there's again, it requires the autonomous decisions of two agents in order to create a binding. Now, what I do is I treat these bindings as information channels, somewhat like Shannon information channels, where the alphabet of possible states is the overlap of these sets. What you can do with that, of course, is recreate space and time as a network, discrete network of agents talking to other agents over information channels, which are in principle unidirectional information channels. But of course, by symmetrizing, you can create bidirectional channels and recreate essentially Cartesian space-time in the limit of some kind of graph formed by agents. The difference, of course, is that you still have interior structure at every point. So Euclidean space-time has featureless points, but agent space-time has featureful points or functional points. And of course, these can have semantics. So I call this semantic space-time. It's basically graph theory plus plus. But to cut a long story short, what's very interesting about semantic space-time is that when you try to discuss things like motion, which we take for granted in Euclidean space-time, Newton's story about things moving with position x and t, position x, y, z in a certain time. and velocities and vectors and all of these things. That's a totally externalized view of change. But in a semantic space-time world, the idea of motion is very interesting because it requires you to have states, interior states of agents, which can then be somehow transported, teleported to other agents in order for a promise to move from one agent to another. And it turns out that there are three kinds of motion that can be distinguished. And I won't go into that, but you can dig into it. Motion of the first, second, and third kinds. And basically motion of the third kind is what we think of as somewhat Newtonian-like motion, where a promise now can move from agent to agent. And promises externalize things, so they are like the properties that we can measure in physics. So you can imagine something like an agent which makes a promise, I am an electron. And this promise is moved from agent to agent, where the agent is now the space-time point. And the motion of an electron corresponds to the movement of this promise being passed from agent to agent, sort of handed down along these Shannon channels, if you like, by voluntary cooperation of these autonomous agents. Just let that sink in for a second. Now let me make a simple observation. Although we've been kind of drilled to think about motion and physics in terms of Newtonian's ideas, external space-time, bodies, motion of things in a straight line, and so on, this is actually the exception rather than the rule in systems of how motion takes place. When you pay someone money through a financial network, your dollar bill doesn't continue to move in a straight line until somebody, impacts it with another dollar bill. It goes from one person to the next and it stops. It's accepted and done, finished. Similarly, when proteins are passed from cell to cell, it just gets passed from cell to cell, doesn't continue to pass through all of the cells and zoom off into the distance. So Newtonian mechanics is the odd one out, even though we think about it as the universal truth, right? What semantic spacetime describes is, in fact, everything else. So yes, we can recover Newtonian spacetime in a limit, but actually it describes biology, financial system, computers, of course, virtual computers, inside physical computers, because now agents can be inside other agents. We'll call them super agents. By just putting boundaries around things, you can create agents with some locality or autonomy. And this corresponds to the physics notion of locality. And of course, locality, very important in quantum physics. And yes, the answer to your question, I can see you're all thinking this, how does this apply to quantum mechanics? Well, if you try to describe motion in a world of agents and virtual agents, it ends up looking very much like quantum mechanics for very good reasons. And the reasons are basically that all of the weirdness in quantum mechanics can be explained away by having interior degrees of freedom at points. And the fact that we insist on having all of the logic or all of the semantics externalized in Newtonian physics makes for all kinds of trouble and leads to these inconsistencies. Just last month, I created an explicit model of quantum entanglement, the Bell experiments, and showed that you can reproduce all of those results in a very simple way with a very simple model using a discrete space-time, a very simple reduced alphabet of states, and generate all of the nonlinear apparent quantum weirdnesses of quantum mechanics just by trying to transport these processes rather than things, and have these things interact with one another. So again, I don't want to go into the details, but what I've been doing is applying this idea of semantic spacetime, which is a promise theory-based spacetime, where you have interior and exterior promises distinguished from one another, and processes that are responsible for keeping these promises on the interior and the exterior. And then looking at how these things scale. So as you know, physics is really all about scaling. You take some things and then you put them together, you compose them, and you say, can I create something similar at a new scale? So we put protons, neutrons together, create a nucleus, an atom. We put some atoms into a molecule. The molecules can move around. They can create a new physics. They can join together into a solid or crystal that can create a new physics. So at every scale, there are typically new phenomena or new promises that can be kept, new processes that can be represented. A bunch of resistors and capacitors can become a radio or a TV or a computer and so on. So the scaling of dynamics that we're used to in physics can be extended to include the scaling of semantics and all of the languages of cooperation, which are alphabetical, set theoretic, and so on. And we can describe virtual motion and physical motion as virtual motion and encompass the whole thing in this story about virtual motion. Now, I've kind of written this story as a set of lecture notes, which I will include into the minutes. And I've been thinking about how to write this or publish this in some way. It's a very long story because there are a lot of details, but it's a very simple story. Surprisingly simple, actually. So physicists are going to hate it because it's much too, with a very simple active legerdemain, we can suddenly explain all these weird things in physics with a very simple story, which doesn't require hidden dimensions. Although you could say the interior of these agents are somehow like the hidden dimensions that you need if you insist on externalizing everything in string theory. So there may be a connection there too, but I don't know that yet. One last point here, which goes back to Jan's original ideas about trust. The very last thing that I got interested in was this connection that Jan and I discussed way back in 2006 about had the role between trust and promises. So we call this promise theory because in the limit of large agents, humans, the idea that agents can advertise their services or alphabets or menus of Happy Meals to one another is somewhat like promises that we make in the human world. So in the limit of human scale, all of these things kind of look like what we know of as promises. And underneath that, there's something called trust. Of course, on the very small scales, where we have electrons and so on, my world, we have energy. And energy is really this fictitious quantity that we've invented in order to count systems and to make them quantitative. What we try to do in physics is to suppress semantics as much as possible because we want physics to be universal, quote unquote. We want it to be objective, quote unquote. So we don't like there to be anything localized that could be subjective or different or inhomogeneous about the world. So that's kind of why physics tries to be quantitative and only quantitative. But there are still semantics buried in physics, which in the forces between particles and the kinds of interactions they can have. But we try to basically end up by counting these things and turning them into this quantity called energy. So the semantics now lie in how one kind of energy turns into another kind of energy, and we pretend they're all the same ultimately to make it easy. And this is basically how money works as well in financial services. There are all different kinds of money, property, dollar bills, pounds. Are there still pounds? I'm not quite sure about that, but there may still be pounds if they haven't shrunk to zero yet. Sorry, James. But these, of course, can all ultimately be interconnected as well through various semantics. And basically every country is an autonomous agent in the financial system that maintains its own promises. And it's through the cooperation of these things that we can exchange money between different countries, because of course money is entirely local. But anyway, all of these things, so we have a hierarchy of scales from the very small to the very large, with agent-like things, with interiors that communicate with one another through exterior channels and create all kinds of interesting cooperative structures. We count on the small scale in terms of energy. How do we count on the big scale? My hypothesis has been that trust is the quantity that behaves somewhat like energy on the social scale, the sociological scale, for promises in the human sense. I've had this in the back of my mind for many years, that might be a way to understand trust. And I was interested, could we formalize that idea and show that the counting kind of works and makes sense? And so I've now written another huge set of notes to show that there is a story in which the counting of trust can be formalized, and the counting is exactly the same way as we use to count energy. And there's a bunch of correspondences, like momentum turns into influences, and there's a renaming of things, as there always is when semantics change. But the renaming underpins what Newton would have called dynamical similarity or similitude, where the idea, of course, is that similar systems may have similar explanations. So my question that I've been looking at these past years is there a story about trust and promises that scales from the very small to the very large? And the answer seems to be yes. And it seems to be that what we call energy on a small scale, which has very simple semantics, translates into something with more complex and varied dynamics on larger scales, moving through things like money into things like trust. And basically, money is a proxy for trust, as we understand it in social systems as well. So these things are sort of consistent. So I can stop there and just say that's what I've been working on. And promise theory, in a rigorous sense, makes this story consistent and extremely simple. But of course, each time we go up in scale and add to the complexity, all kinds of other complexities can come in. And I'm intrigued by the stories that I've heard about these transets and totalized algebras and all of these things. I've been intrigued for a long time, and it goes a bit beyond me. But I'm increasingly trying to explain to people in physics that the big omission in physics seems to be, in my mind, that we have forgotten about the distinction between what's inside and what's outside, what's visible or observable and what's unobservable. And we're so obsessed with this notion of points because of the traditions of Euclidean, Riemannian spacetime, that we've forgotten about the existence of potentially interior degrees of freedom, which could be important. So there's a story of the world in which agents play a key role. And that's what I've been doing.
Okay, thank you, Mark. I have three immediate thoughts. The first is that promise theory is offering a tool, an analytical tool to deal with reductionism. So you're facing up to the problem of how do we get from fundamental particles to the galaxy, passing through human and biological societies along the way. So as I said to Jan, I see promise theory now as developing into a tool of analytical philosophy. Who knows if that's the right way of thinking of it. The second thing I wanted to mention is that transreal arithmetic has been used to extend Newtonian physics so that it applies at singularities. So we can solve Newtonian problems exactly at singularities. because we've now totalized the whole of mathematics, we know that we could extend all of the mathematics that physicists use so that it will work at singularities. And then the question is, are there any physically interesting cases where singularities occur that we can analyze and make predictions that couldn't otherwise be made? And it's very hard to see that there are any in macrophysics. In macrophysics, the world usually goes wobbly as you up the energy long before you reach a singularity. Conceivably, we have something to say about the singularities in a black hole, and that's published. Steve has suggested that the place where we're most likely to find physical singularities that are analyzable with transreal arithmetic is in quantum physics, because systems move from one state to another. There's no opportunity to go wobbly in the middle. So let me just flag that quantum physics is interesting to people developing transmathematics. So quite apart from promise theory and reductionism. There has been, so moving to my third point, there has been quite a lot of investigation and theorizing about the evolutionary basis of trust. And essentially, trust increases survivability, and people have looked at how trust is carried from the individual to a group of kin out to a bigger social group. And in this case, trust converts to lifetime, to survivability. It converts to social enterprises. Let's build a pyramid. Well, there's a lot of energy and rock and matter goes into building a pyramid, and all of that rock gets moved as a result of trust. So it's interesting that you've identified trust as being a metric of promises.
You know, this is very interesting to me on another level. Next week I'm off to Kavli Institute in Los Angeles, a neuroscience research place. They're interested in my ideas about space and time in connection with neuroscience. You know, in the brain we have cells that have evolved to map out the world both in terms of coordinates, grid cells, and in terms of semantics or landmarks, place cells. So there are these specialized mechanisms for detecting space and time in different ways. And what premise theory sort of ends up saying about the world is that we need to think about processes not as these Markov processes that we've been very fond of in physics, which tend to come about because of the ballistic origins of physics in Newtonian spacetime. Because points are featureless, they can only smash into each other, you know, and like a game of ping pong or something. But when we get on a larger scale, you have memory processes, so hysteresis, balls that can deform and shapes that can change, that can remember their state over time. If we think of every process as a memory process, where memory is maybe inside or outside an agent, then the world starts to make a lot of sense as well. So certainly interior memory helps to explain things like quantum entanglement, but exterior memory, so-called stigmergic memory, you know, that like ants leave pheromone trails around and society leaves books and libraries around to pass on knowledge. We externalize a lot of our learning in order to perpetuate processes beyond the lifetime of a single agent. So language is a great example where language couldn't be rediscovered every time a baby is born. Its image stays in the environment around it, and we pick it up from stigmergically from where it was left off by the previous generation and so on. So we see these processes happening on all kinds of scales with interiors and exteriors. Quick comment on your first point. For analytical philosophy, I think that's certainly true. Jan has always been interested in the philosophical side of the questions and has often contributed those kinds of insights. I always try to pull us back down to the nitty-gritty nuts and bolts, because I'm a physics guy by nature. But that interaction I've found to be extremely powerful, and it's that philosophical input that Jan has often created that has tested the viability of that nuts and bolts approach that I've had. Jan, you're on mute.
Yeah, bye-bye, Jan. You're muted. I think he's just going.
Okay, okay. So yes, I think, promise theory for me was just something I thought might last a couple of weeks when back in 2004, but now it's kind of taken over my life. It seems to have something to say about a lot of different issues.
Yeah. I mean, it's an interesting formalism. Does anyone else have anything they want to say? No? Okay, well, I think we'll wrap it up then. So, oh, Walter, do you have anything you want to say? No? Okay. Well, thank you everybody for attending Transmathematica 2022. Look forward to next year's conference, which will certainly be online. I don't know if the COVID situation will allow a physical meeting or not, but we'll find out.
Glad that you're feeling better now, James, and thank you for arranging this.
It's very, very slow. It's been months, but I am getting better all the time. Right, thank you everybody. Bye-bye.
Bye-bye. Good to talk to you.
Yeah.